And typically, you have so-called learning tools offline approach. So you have the training data sets, and then you use this kind of data sets to train your engine, and then you can predict the future. But the thing is that this kind of data often biased. And even worse, for social networks, they're often outdated because this is a very dynamic system. The things change rapidly. Okay? If you think about video propagation patterns and user watching behaviors and sharing behaviors. So you have to deal with this kind of dynamics. And second, most of those solutions focus on accuracy. So the idea is that you are given data and you predict. And when you do predict, you try to maximize the accuracy. That's good. But on the other hand, another dimension you often ignore, that is the time. Okay. So if the propagation finishes or take a long time, then by that time, your prediction, of course, you know the result. That's good, highly accurate. But on the other hand, think about the advertisement. Think about the resource reservation. Of course, you want to do that as early as possible. So you have to consider time in this long propagation process. And you want to make an optimal trade-off between prediction, accuracy, and timeliness. So there have been some works along this direction. And most of them are view-based. So you have the history of the past view counts. And this is often related to the inherent attractiveness of the video, the content-based. Okay? But when they do this, they often ignore the context information in the social networks because the videos are propagated in the social networks. So who initiates this kind of video and who shares this kind of video? Well, those information often ignored in this kind of models. So you need to use this kind of model to have a better prediction and more timely prediction. So that's what we want to do. So here comes our solution, so-called social forecast. Well, we basically formulate this problem as a multi-stage sequential decision and online learning problem. And we try to make the best trade-off between accuracy and timeliness. And we design a good algorithm. And we show that we can guarantee the performance in some sense. Okay. And then we validate this with the real-world trace data from various social network, and we show improvement over the existing solutions. So here is the overview of the system before we introduce the detailed algorithm. So we have this social media start from some initiator, propagate video. And then we have this kind of contextual information from the social network and fed into the popularity prediction engine. And this one predicts whether a video will be popular or not. So you do this along the time because propagation takes time. So from age 1, age 2, so on and so forth. You want to get the result before this threshold, capital N. And the earlier, the better. But on the other hand, maximize the accuracy, because if it were too earlier, then the accuracy would be sacrificed. So that's a trade-off. And know that in the end, you of course eventually knows whether this is popular or not. So you know the true realized popularity. So this can be used to calibrate this prediction engine and making this one better and better. Okay. So that's the system. And let's see how do we model this. Well, we assume that videos arrive in sequence. And we start from video 1, video 2, so on and so forth, indexed by K. And you have a discrete time model, a period, can be a minute, hours, days, depends on your application. And you have age n if it has been propagated for n periods. So you want to predict the popularity by age n. That means by age n, this capital N, this time, you want to know whether at this time, this video would be highly popular or not. For example, one measure is the total number of views. It exceeds a predefined number, but you can have many other views and better granularity. Okay? And you need to make this decision as early as possible, but as accurate as possible. So that's the idea. And know that when video propagates in social network, in fact, you have the context in social network. So you have this context information for video K at age n. This belongs to a context space high n. So you first have the context information for period 1, but then over the time you have more and more context information. The context information is a generic thing. You can have many different context information. For example, simplest you have only views. Okay? But in the social network, you could have the initiator's position, and you could have a so-called function factor, DRF, the number of viewers that can follow the starter or the share. And the share rate, the ratio of views that reshare the video after watching, it depends, of course, on the content of the video. And you could have many others. These two are widely used. So here's just an illustration of this, although we can have many other context information. Okay. Say you have video 1, we know that eventually this one is not that popular. Video 2 is very popular. Okay. And it turns out that if you look at video 1 and video 2, they have similar sharing rate. 1 and 2, similar sharing rate. But 2 has much larger branching factor. So that leads to the popularity of high popularity of video 2. And on the other hand, if you have video 1 and video 3, they have similar branching factor, but video 2 has much larger share rate, and this also makes video 2 highly popular. So you see, it depends on many of the factors, at least in this case, 2-dimensional factors. So we want to predict this, and at age n, we want to have an action. And this action, either you can make a decision, forecast whether this is popular or not, or you just wait to the next period. Okay? And the policy at age n, we define this as from this context space at age n to this action, either prediction or wait. And then we have the complete policy space from time 1 to time n. And we also have a reward per age. So this reward is a utility function between your action and the true popularity, assume that we know it, okay? And also your age. If you make a prediction, or if you don't make a prediction, you try to postpone your prediction, then this will be equal to the next time's reward, okay? So this function depends on both accuracy and the timeliness of the prediction. So this is a function of accuracy, the theta, and phi, this is n, and with some weighting factor. And your overall reward depends on the first time you issue a forecast. Okay? Now basically says at this start, and you have issued a forecast, then this is your overall reward. And then your expected prediction reward, given a policy, then is this V pi. And your objective, of course, to find out this pi that maximize this reward in terms of accuracy, in terms of time. Okay? And if you look at this, in fact, if you list all the factors, you find that the solution depends on the probability distribution of fx, that is the video context information. Okay? If you have this context information, actually you could solve this optimization problem and get a good prediction. But the thing is that this context information, in fact, is not known in advance, and that said, it needs to be learned over time and over the videos. A key observation here is that if the videos that propagate in social network, they have similar context information, then they would have similar popularity. That said, we can have a sub-problem that we fix this pi minus n plus the policy before time n, then we try to learn this n, the best one, okay? So again, there are some alternatives. So you can have estimation without using the context information. You completely ignore that. Then, of course, you don't have to rely on fx, then you can solve it. But this is indeed the old solution. It's inefficient, does not consider social network. And secondly, is that you count every context information. You search the whole space. Again, this space can be big, and this is inefficient. Okay. So our solution is basically, as said, to explore the similarity, and then we partition the context space and learn it over the time. So here is the thing. Now we initially have a big context space, and you have something arrival, the video arrival, and then you try to find out which subspace it belongs to, and using the previous information to predict it. And get the action with the highest reward estimate in this context. And when later this popularity is realized, then you can update your estimated reward. And this makes the space finer and finer. Over the time, you can partition, okay, and then get better estimates. So for detailed algorithm, you can refer to this. Even the given time, I tell you that you do decision making based on current estimate, and then later you can update the reward, and based on that, you can make the system better and better, the space, subspace, finer and finer. Okay. So to evaluate its performance, we can show the learning rate, and this is basically what you learned and compared to eventually realize the thing. And there are some tedious derivations. What I can show you is that over the time, when you have more and more videos, this is the number of videos, then this will rate. I mean, you will get better and better prediction in terms of accuracy and in terms of timeliness. So that's basically the algorithm framework, and we have evaluated through trace-driven simulations using the random data. And in this data, we first start from a cost popularity rank. So say we define the total views exceed 10,000 as popular. And otherwise, it's unpopular. And this is based on just the empirical data. There's other data. Define your own threshold, depends on your application, depends on your data. And we have the reward function defined as this. This is the accuracy, this is the timeliness. So we differentiate false positive and false negative with different weights. And of course, if your prediction is wrong, then you have zero reward. And the time is whether you're approaching the end, that's factor end. Then we have several benchmarks. We have the pure view-based SH algorithm. We have the PAT also, advanced view-based algorithm. And we have some variation of them, which tries to incorporate the context information, CC, and then we use them to do the prediction. And this one just shows the result. Say, if you look at this social forecast algorithm, the accuracy can be pretty high, okay? And with different weights for the timeliness. And also, you have different lambda. Again, in any case, ours are much better than other existing algorithms. And even better, over the time, our prediction can be more and more accurate. For others, they remain the same because they don't have this context information and don't learn it over the time. And that's just a two-state popularity. We can have finer granularity. For example, we can have high, medium, low popularity. Again, ours are much better. Okay. And in terms of both different lambda and different omega. So that's basically all of my presentation, and we have some systematic, high-efficient online popularity forecasting algorithm for videos, and we incorporate the context information. Actually, this can be used in many other things, not just the video, but video is a good case. Okay. And we are also considering some future works for example, distributed multi-engine forecasting, and we also do product transfer. As you see, the last author is currently project leader in Hisense company, the major TV manufacturer in China, and he's leading the video recommendation subsystem. And we are trying to incorporate this algorithm into the system. So that's all for my presentation. Thanks.
Thanks for Professor Zhang Chuanliu's wonderful presentation. Are there any questions?
Okay, so basically, I said the video recommendation system traditionally, most of the cases, they're based on history data, and they collect history data, not online learning. And also, they most likely consider the attractiveness of the content, whether content is interesting or not. Not necessarily social networks, but what we are doing actually considers those social networks. And in fact, in the Hisense TV company, they are building the set-top boxes. And in those boxes, the TVs can be interconnected, and they can propagate this kind of interest. And that builds a social network, and in which our algorithm can be used. Yeah.
Okay. Are there any other questions? Okay, let's ask questions to Professor Zhang Chuanliu again. The second presentation will be given by Christopher Britton from Princeton University. He is a PhD candidate at Princeton University.
One second, sorry. That's the working fine before. Hey, sorry about that. Thank you guys for coming. Today I'm going to present to you my work on MOOC performance prediction via clickstream data and social learning networks. And this is joint work with my advisor, Meng Chang at Princeton University. So first I'm going to give a little background behind the problem that we're trying to solve here. I think most of you know what massive open online courses, or MOOCs, are, so they've been around for quite a while now, actually. But just to give you a brief overview, these are course offerings offered by platforms like Coursera, edX, Udacity that are partnered with major universities, which have tens, hundreds of thousands of students in single offerings. And they all commonly offer different learning modes to students, like lecture videos, which are really the most popular ways that students like to learn in these courses, assessments, and of course discussion forums for peer-to-peer interaction and learning from each other. And so what we see emerge from these and also other learning scenarios besides just MOOC are social learning networks, which are networks that form between learners, instructors, and modules of information. So this this has to model the dynamics that occur between learners and instructors, and importantly for this paper, between learners and modules of information and trying to digest information material. And today, there are a lot of issues that are faced by SLN and MOOC, which has been an issue, at least for MOOC being able to make a higher penetration into higher education. For example, the scale efficacy trade-off. So as enrollment goes up to hundreds of thousands, even at the envelope of this curve here, which is plotting the completion rate and percentage of open source data, we see that the completion rates are going down, and also just lower engagement in general without having in-person interaction like in traditional classrooms. So what we're studying here is a very fundamental question related to this, which is, can we relate behavior and performance? So behavior being, for example, in the most common learning mode, how students watch videos, and performance being, for example, how they answer assessment questions. So the two questions that we pose here in this paper, Q1, is it possible to correlate student performance on assessments with their video watching behavior? And then if so, Q2, can we use student behavior in an online fashion to actually predict their performance better than without it? So just to give you an idea of the scenario we're talking about here, we have students that are watching these different lecture videos, interacting, pausing, playing fast forward, rewinding, watching whatever portion of the video they decide to watch. And then we want to see if we can use that behavior to actually determine whether they're going to be correct or not on the corresponding question. So CFA prediction has been studied. CFA is correct on first attempt. These types of prediction problems have been studied for traditional education settings without any type of behavioral data. But this MOOC, of course, brings a lot of more questions to the picture. So two sets of data that we're going to use, quiz submissions to quantify student performance. I have about 40,000 of those over 92 videos from about 5,000 users. And if you build the user, just in your mind, the user video matrix here, each video has exactly one question. This is all data actually coming from our first ever MOOC offering at Princeton in 2012. But if you do build that user video matrix, you're only going to have about 8% of the entries filled. So that really underscores the sparsity of the problem here. Similar to, for example, when you're trying to predict what users are going to rate movies in the Netflix type of problem, trying to predict their ratings between 1 and 5. It's a similar scenario here. Whereas in traditional education settings, everybody's required to take all of the quiz questions. So you have 90, 100% of your entries filled usually. And the second one, so quiz submissions are a quantification of performance, and clickstream logs are a quantification of behavior here. And we have about 1.3 million total recorded. So taking a look quickly at the submission counts, these two plots here are showing over users, the empirical CDF of the submission counts, and over videos, the empirical CDF. So basically, how many submissions are received by a proportion of videos. What we can see right away is there's kind of a heavy tail effect here, where less than 10% of users are making 50% of the submissions, and less than 12% of the videos are basically the first week of the course is receiving about 50% of the submissions. So that's, again, underscoring this this completion rate or drop-off issue, where there's only relatively few active users relative to the whole course population, and there's a drop-off over time as well, with people sort of losing interest. But if we only consider active users in the course quizzes, which is what's done in the black trace here, the distributions become a bit more uniform. Looking at the CFA scores themselves, again, we're only concerned with the first attempt, because any future attempts, the same questions, are not just related to whether the users digested the information or not. The average is 0.658 over all submissions, meaning that we're slightly biased towards the correct. This completely random would be 0.5. So if we predicted all ones, we would get 65% accuracy in the predictor. And we'll actually use that as a baseline predictor a bit later and try to measure incremental gain over the top of that percentage. So looking at the clickstream logs in a bit more detail, each event that a user makes is triggering these click logs. These come in the forms of either play, pause, rate change, or seek events. So if you've never seen a MOOC video before, just picture yourself on YouTube changing the rate to be faster if you're bored of something or skipping forward, backwards. And what we do is we basically have these user video pairs, which are associated with clickstream logs as well as the quiz submissions, whether it was correct or incorrect. So we need a way to summarize behavior to try to relate that to performance. The approach that we take in this paper, which we've since extended in a more recent submission, is to compute behavioral quantities, aggregate quantities. And these quantities are probably intuitive ways that you would think about how you would look at a way someone watched video. These are quantities like the fraction of video that was played, the fraction of time the user spent paused relative to the length of the video, the number of pauses the user made, the average playback rate, as well as the standard deviation, whether they actually varied the playback rate at all or not. The number of rewinds, so if they're going back to revise something, or the number of fast forwards, just a few examples. And what we do is we split the correct on first attempt and the not correct on first attempt into binary classes, and we analyze the distributions to look to see if we can find differences in performance. And so even by looking at just the averages, we can already see some statistically significant differences here. So for fraction played, number of pauses, and number of rewinds, the average for CFA is statistically higher than it is for non-CFA. But these averages don't really tell the whole picture. We dive into a little more detail and look at the actual distributions. We can identify more substantial differences, which lead to insights into how people learn a little more. So what we do in order to do this is we compute intervals of these video watching quantities. So we compute the probability density functions, the probability mass functions, and we try to look to see whether there are differences in ranges between these values. So I'm showing here basically two continuous quantities, fraction completed and fraction pauses, two of the interesting cases. The black curves are showing the non-CFA, so the incorrect submissions, and the green curves are showing the CFA, or the correct submissions. And what you can see right away is that there are visual differences between the two density curves in each of the cases. So if we look at the fraction pause example, we can actually trace through it and assign equations to these different measures. So if we're below about 0.05, we see that CFA is higher, so higher than CFA. So that means that the user is really not pausing very much at all. Pretty confident with the system incorrectly. Then after we go above about 0.1, we actually have a higher tendency to be not indicating there's a little more confusion there, so causing them to pause a bit more, spend a bit more time paused, but not enough so that you actually get the question correct. Not until we get to about 0.25 or a little bit above, which is pretty substantial, where even if the person was confused at first, if they're pausing more, then they actually tend to be correct because they're gaining information. And then finally it switches again, even though we're getting to lower density and understand that. Up at the top here, where things tend to go the other way again, and that's indicating a lot of confusion, basically. Maybe the user needed to have the material presented in a different way. So we can run statistical analysis as well to make this more concrete. What I'm giving you here are the most discriminative quantities as well as the respective intervals of identifying differences between CFA and non-CFA. We look, for example, at the number of pauses here. This is basically saying if number of pauses is either 0 or 1, higher chance of being incorrect, the success probability is 0.42. So it's about 8% lower than just random. And if it's above 1, so 2 through 10, higher chance of being correct, and then you have about 0.567. Take the difference between the two of those, that's about a 15% total differential there, which basically means that switching between those two sets, you're actually changing the CFA probability by 15%, which is pretty remarkable. And all of these, of course, are statistically significant, and similar intuitions apply for the fraction played, standard deviation on the playback rate. So if people don't vary it at all, where the standard deviation is 0, higher chance of being incorrect. If they do vary it somewhat, they have a higher chance of being correct. Saying you actually make an effort to interact and move things around a bit, then you have a little more than 6% difference there. And so you can extract some measures here, basically saying which behaviors have a higher chance of being CFA. And there's a lot more details here in the paper. So what I want to do for the remainder of the talk, that was Q1, basically. The answer is yes, and we can correlate behavior and performance. They are significantly correlated. Then we want to generalize this in a sense and try to see if we can actually use this to predict performance in an online fashion. So in order to do this, we're going to define core sequential components of this procedure, and we're going to learn this over training sets, so training test set partitions. I'll talk a bit more about how we do that through cross-validation later, but the first part of this procedure is the density estimation. So for each of the quantities over the training set, we have to, for each of those 8 or 9 quantities, we have to estimate the densities for the 2 different classes. For continuous quantities, we use kernel density estimation with a smoothing parameter of gamma that we're going to introduce. And for discrete quantities, we just compute the PMF directly. And what we're left with are these curves here. Basically, over the values of the quantity, we have how the densities vary. Then, for each quantity, we do interval extraction. So we want to find the intersection points between the changes in density, which in turn define the intervals. Here, we just have 3 different intervals which we can obtain. Then we do the CFA estimation within each of the intervals. So we want to look and compare the fraction of samples that we're obtaining for each of the different curves. And what we do in an online fashion here, normally intuitively you may think that if you would just look at the number of CFA samples versus the number of non-CFA samples. It gets a bit more complicated with Bayesian probability. You just apply the Laplace's rule of succession. More details there in the paper. And then once we have the estimate for the success probability, we in turn apply Bayesian adjustment with a population weight of sigma. The idea behind Bayesian adjustment here is that within each of these intervals, there's going to be a different number of samples that we have. So some of the intervals may actually have a very low number of samples, and therefore we want to compensate for that and not overfit on the training data, therefore pull things closer to the population mean 0.5. There's actually a trade-off, which I go into more detail in the paper, between this population weight sigma and, in the case of the continuous quantities, which is the majority of the quantities, this smoothing parameter eta. So when eta is higher, we're going to have smoother curves, and we're going to tend to have less intersection points between them. So there's going to be a smoothing effect over here. That means that we're generally going to have more samples within each of the intervals. Therefore, that would allow sigma to be able to be smaller to still obtain good results in a general fashion. Whereas if we choose a lower value of eta, we would have to have sigma higher to be able to compensate for the fact that we're going to have smaller numbers of samples in different intervals. The final step is learning features. Basically, for each of the samples now, we're going to go through each of the samples and compute success estimates, which are going to become learning features for each of the sample. So if you just look at the design matrix down here, what we have, basically, each of these rows is one sample, so one user video pair. We have an indicator feature for which user it is, which implicitly incorporates bias there. So if some users tend to just answer questions more correctly, they'll have higher biases. That's incorporating that. Quizzes also, we're going to have biases associated with them. Some quizzes may generally be harder, which would lead them to have lower CFA scores. And then the behavioral information is in the right-hand side over here, these clickstream features. So we have 8 of them in this case. And what we do is for each of the samples, we figure out which of the intervals each of the different quantities lies in. And we use the success estimates in each of those intervals as the values in this matrix. And then we take that and we want to relate x to y. We apply a support vector machine, SVM. We use a polynomial kernel on top of that. Of course, there's a lot of parameters that need to be tuned here, so I'm really abstracting, sort of giving you 50,000 feet view here. A lot more details in the paper. We did try a lot of other machine learning methods as well, like decision trees, neural networks, standard logistic regression, linear regression. SVM tended to work the best for this application. So for the evaluation, we'll use some standard metrics that are applied in collaborative filtering. Accuracy, which is just a fraction of the test set that are predicted correctly, so you obtain the predictions around them to 1 or 0. RMSE, which is going to use the real values rather than rounded predictions. And AUC, which is just the area under the ROC of the classifier, basically evaluating the trade-off between the true and false positive rates. The standards that we'll compare to are algorithms that have been used both in CFA prediction for traditional education settings, as well as other collaborative filtering applications like the Netflix prize competition. K-nearest neighbor, where we're in essence finding user-to-user similarities and applying those. Biases, where we assign biases to each user in quiz, and the intuitive, there's an optimization involved there of the logic functions as well. But basically, each user in each quiz are going to have a bias, and you add them together to form the final prediction. And then also matrix factorization, which takes it a step further to actually assign latent factor vectors for each user in each quiz. You take the inner product of those to form the final prediction. So the important thing, though, is that these standards, these 3 standards that we're going to look at, do not use behavioral data at all. And this is what is typically applied in traditional education settings. So to obtain the prediction results, again, this is an online procedure, so we have to run standard prediction. There's also a lot of tuning going on here, some grid search, because there's a lot of different parameters that each of these different algorithms. And I'm abstracting that here as well. But basically, we apply cross-validation. We use five-fold CV, which is basically dividing our data set into 5 different partitions. And we run 5 different cases where we treat 4/5 of the folds as the training data and 1/5 as the test data. And we average and we repeat the procedure randomly allocated as many times as we can so we can get the most results. Now, it would be possible also to think about this in terms of trying to predict like the next quiz submission, so then the test data would become just the values in the future. But MOOC is inherently asynchronous by nature, so you have people taking quizzes a lot of different times. So really the most general way to do it in this case is just to randomly choose what's going to be in your test set versus your training set. And these are showing the results over the full data set. The first 3 rows here are the standard algorithms, and the last 2 are the algorithms that leverage the clickstream behavioral quantities. The difference between vid-n and vid-a, vid-n is not using that final Bayesian adjustment portion, whereas vid-a is applying that adjustment to evaluate that trade-off between eta and gamma, as I was discussing before. And as we can see here, the video watching quantities are doing better in each of the cases. If we dive into a bit more detail, though, what I'm doing is here I'm looking at 2 different partitions of the data set. Going back to the beginning where we were talking about active users and the first few quizzes. The top right here, the top row, these are plotting the percent improvements relative to a naive baseline of just predicting the average in the training data. So, of course, all of these algorithms are obtaining improvements over that. The top row here is showing active users over the full course, one partition. The bottom row is showing all users over the first 2 course weeks. So you can see in all of the cases, the incremental improvement for the video watching algorithms is higher. But what's really interesting and what we found to be probably the key takeaway from this work is that the improvement with our algorithms is particularly pronounced when we're considering these first 2 weeks or the beginning of the course. And the reason for that intuitively is that it's not yet clear at the beginning of the course who the active users are, right? So these other algorithms, these other standard machine learning collaborative filtering algorithms that are trying to apply this prediction method don't have this extra clickstream data. It's not clear who the active users are. It's harder to run these prediction methods. It's really important to do prediction early on in the course as well, because this is the time, going back to our whole problem statement in the beginning about trying to improve the efficacy of learning on MOOCs. The time in the beginning of the course is the most important, because that's when instructors would need to figure out what quizzes are going to be particularly difficult or what users are going to be struggling particularly much. So we consider this to be a very promising result, at least in terms of being able to give methods to instructors to be able to help out students as well. And so this early detection is the key takeaway here. So key findings and contributions, again, just to summarize, Q1, is it possible to do correlation? Answer, yes. We found student behavior is significantly correlated with the performance. And Q2, can we use student behavior to predict the performance better than without it? Answer is yes, but there's also an addendum there that the behavioral data is particularly useful for earliest detection type of prediction. Really quickly, I'd just like to give you a quick application of this here, because we are working in conjunction with a startup company, actually in deploying some of this. And we want to be able to reveal detailed learner and content analytics to instructors to see if they can actually make use of this type of information. So I sort of alluded to this before, but modules in an instructor dashboard that would be given to a MOOC instructor that would be able to utilize performance prediction would include, for example, modules that are trying to cluster students and content based upon similar performance. And also pairing study partners, right? So if you think about MOOC forums, there's a lot of different people, tens, hundreds of thousands of people. Sometimes it's hard to figure out who the best person may be for you to study with. But if you have 2 sets of users who are actually quite dissimilar in their performance, so one user is doing well on certain quizzes, not well on others, and the other users, the opposites, are doing well on the quizzes that the first users do not do well on, they may make really good study partners. And so here's just a screenshot of some visualizations that we are working on today. Okay, that's it. Thank you very much. Do you have any questions?
Any question?
And I can see there's a matrix X, right, in the presentation. So in some of the column, in the first few columns, is correspond to user.
Correct.
So does it mean that you embrace a social network in X?
Those are actually indicators. You could. That's really good. I think you could actually use that in some sense. Here, though, I'm not. I'm just using that as indicator variables. But I think you could. It's actually a really good point. Thank you.
Any other question? Okay, thanks, Christopher. The next presentation will be given by Felix Wang. He's Dr. Felix Wang. He's also from Princeton University.
Hello. Hi, everyone. Welcome here today. Today I'm going to present the paper on the efficiency of social recommender networks. By the way, I'm not a professor anymore. I'm now a software engineer. So a little bit about the background of this research. The research agenda in our group is to try to find ways to apply context optimization techniques to study data, analyze data, in particular studying the problems in information networks. And this work is one of the works in that line of work. So here we look at two things. First is recommender systems. Everyone knows what they are. We use it every day. Amazon, Yelp, Netflix, New York Times. The performance of the recommender system is crucial to the so-called digital economy. And in recent years, there's a trend in using social networks in recommender systems. For example, you use a product and then you like it. So you post a post on Facebook, for example, saying that you like the product. And a lot of e-commerce companies, they would like to use this word of mouth effect to try to sell more products. In particular, Yelp has this news feed thing that people review a restaurant and then your friends on Yelp will also see it. So there's one question in the social networks that's quite interesting is so here social networks are usually formed in a decentralized manner, organically. What it means is every pair of users have the freedom to create or become friends or not. So intuitively, if we have a mechanism like this, we're not really sure whether a social network like this would be good. And what we mean by good, we consider two things, which we call the local utility and the global utility. Local utility means so you make some friends, you get some recommendations from your friends. Your local utility is whether the recommendations you get from your friends are good or not. And then local utility is a more standard way of seeing the utility of a network. So you want to spread a piece of information. You want useful information to spread the network fast enough so that everyone will be able to gain from it. And the fundamental question in this social network problem is, are local and global utilities compatible? To study this, in this paper, we consider three main questions. first of all, how do we formally define local and global utilities? Our answer here is we start with a stochastic model, and then we try to derive the utilities in terms of equations. And then the second question is, what can we say about the efficiency of real social networks? Here we study real data from Yelp, from the Yelp Data Challenge. And we can calculate numbers, local and global utilities of a specific network. But the question is whether it's good or not. So we need ways or smart ideas to find null models or other baseline graphs to serve as comparisons. And then finally, we are network researchers, so it's interesting to see whether we can optimize a graph in the sense that we can design a network that is good. And in the context of recommender systems or social recommended networks, this can be interpreted as designing algorithms to build news feeds and also do friend recommendations. So let us go through each of the questions one by one. So first of all, local utility. So here's a movie, you like it, and then your friends sort of like. Then we define local utility as the weighted average of the discrepancy you and your friends. And here, the social network we consider is a weighted graph, such that edge weights represent the strength of the tie between you and your global utility. So we use pretty standard notions, the efficiency of propagating information. So there's a lot of work on rumor spreading in networks. So here, what we do, we consider this the average hitting time between every pair of users on the network. And then we did some derivations and consider a reversible Markov chain. And we have an interpretation of this model. And yeah, so then we go to the second question. So we specifically look at the Yelp data set. And why do we focus on Yelp? Because Yelp developed their online social network in-house, so it's not like something that you would import from Facebook or your email network. So we believe it would be a pretty good social network study. And then also the data is very fresh. It's from last year. But we also emphasize that the methodology that we do that we use here is not really restricted to Yelp or restaurants. So we consider two types of graphs in Yelp. First is we already have the Yelp social graph, which is organically grown, as we mentioned before. And then the second is we look at pairs of users, and then we see the similarity between users and ratings. So we have an induced graph based on how similar their ratings are. So going back to the Yelp social graph, it's a pretty large graph of moderate size, I would say. 29K users, 149K edges, has a heavy tail degree distribution. Ratings are mostly positive, so the takeaway is it's not that surprising. And so this is our results in computing local and global utilities of our Yelp social network. So first of all, we consider baselines. These three are based on rating similarity between pairs of users. Graphs designed like these are performing pretty poorly in terms of global efficiency. And then another baseline that we consider is the random graph, just produced from, we start with the social graph. We do edge switch. If we do it long enough, then we get a random graph that is the same and also the same degree for every node in the Yelp social graph. And our finding here is sort of surprising. So the social graph that we observe is pretty close to the random graph in terms of the global utility. So yeah, so the actual graph is quite good. And local similarity, we also see that our social graph is performing the best compared to other graphs. This is not that surprising, but it confirms our intuition that people create the network considering their local utilities. And a little visualization. Top right would be the best. And, the social graph is the best in local utility and a little bit worse than the random graph global utility. We also try to do the following. So our random graph or the normal is created by perturbing the edges. So we consider a family of graphs that have a different number of edge perturbations. And then if we try to plot the local and global utilities of each graph that is generated like this, we sort of see a Pareto optimal or trade-off curve like this. Again, the lower the and to the left, it's better. So it's a trade-off between local and global utility. And then, and then for this one, yeah, we increase the number of iterations, and then the graph that we generate is closer and closer to a random graph. Very few edge overlaps with the original graph. Yeah. So the third question, how do we optimize the graph? So suppose we're able to influence the evolution of the social recommender network. How do we change the edges? How do we add more edges? Or how do we change the weights of the edges? And we can cast this as an optimization problem. Basically, optimize average shipping time subject to everyone's local utility constraints. And our optimization variable are strength of high variable the edge weights W. And we can cast optimization problem like this. And there's a lot of work studying average shipping time. And the takeaway here is that this problem itself is complex, so we can solve it efficiently. But solving a problem like this, the scale is pretty large. So even though it's complex, we still need some tricks to really do it. And so here are two things that we consider. So we try to use off-the-shelf packages to solve. Then there are two problems. First is such packages are not really designed for the optimization problem itself. So it's usually either very slow or it's very restricted such that it cannot really solve our problem. If we code everything ourselves, then it would be very difficult, high complexity, very long cycles to develop. So we take a hybrid approach. We design a projected weighted scenario algorithm, tailor-made, and installate a small number of hard-to-code computation steps. Try to use very fast existing softwares to do it in the right positions. So this is the algorithm. Just loop and the gradient descent, gradient of the hitting time, calculated by this. And then to compute this is actually not that easy. We need to use a fast Laplacian solver. And then after doing a gradient descent, we do a projection so that the local utility constraints are satisfied. And this is a quadratic programming problem that we can apply as fast solvers to do it. The details are in the paper. So this is the result of the optimization. Random graph or the normal is here. The social graph that we see is here. And then if we do optimization, then we can pull our graph to all the way up to here, so that it has almost the same local utility. But on the other hand, it's a much more local utility. And then we also look a little bit into the structure of the graph that is constructed. Takeaways here is, first of all, the degree distribution, entry distributions are changed quite a lot. If you look at this graph here, the original graph has a lot of low degree nodes, and our optimized graph has a lot, shift the degrees upwards, so that poorly connected nodes have higher degrees than before. And then the weight of the edges are being deleted in the sense that they're very small values, 10 to minus 5 or something. And yeah, originally they're ones, so a lot of them became very small, 10 to minus 5, 10 to minus 7. And then a little bit of the edges are also boosted. Yeah, and the diversity of the node degrees are changed or reduced. Since I'm working at Yale, I have to do some motion. Yale Data is a challenge. It's a really fun competition. You get large and rich data for researchers. The deadline is in a few months. Please consider submitting something there. And this is it.
Very interesting talk. Is there any question?
Maybe I missed this. Given that we're dealing with social graphs, I was expecting that the baseline is something akin to a professional attachment model or some of the more classical social network type generators, as opposed to a random graph. That something here.
So we built a random graph in the way that
So how do you mean by random?
it's not inertial.
Okay. Oh, thanks.
So suppose would you like me to?
No, go ahead. Yeah.
It's okay.
I just wasn't sure what you mean random. I thought.
It's not inertial. You look at the social graph. So there are some users that have very few friends. They don't really care about having more friends. They don't use the social network as much. So our edge perturbation mechanism ensures that after doing all the perturbations in the random graph, this specific user also has the same number of friends as before. Preserves the degrees.
But random means not everything. Random means more preferential time.
Something like that.
Okay, any other question? Let us give thanks to Felix Wang. The next presentation will be given by Professor Gianluca Rizzo. He's from University of Applied Science of Western Switzerland.
Okay, so welcome. So the work I will present is a joint work together with Shahzad Alid, Vincenzo Mancuso, and Mark Weimer-Marsan from India Networks, Spain. So the focus of this work is on floating content, which is a communication service which aims at making some piece of information available to mobile users without infrastructure support, but solely relying on opportunistic replications. And it make this piece of information available in a limited amount of time, for a limited amount of time in a geographically constrained region. Applications of this kind of probabilistic geographical storage are in emergency warning services, in some forms of advertising, and in social network kind of applications such as situated introductions. The basic operation of floating content is shown here. Basically, here we have a region that we call the anchor zone. Here is the example is circular. At the center of it, at time t equal to 0, we assume that the user generates a piece of content, maybe a picture or a message or whatever. Then, starting from time t equal to 0, every time a user content is within the transmission range of another user, which doesn't have the content gets replicated opportunistically. So through this mechanism, and over time, number of users with content within the region called anchor zone increase, and hopefully, over the long run, the amount of users with content which exit the anchor zone is compensated by new users which acquire the content and through opportunistic replication within the anchor zone. When this happens in the long run, we say that the content flows, so it's not lost over time, and it persists in this geographically limited region. So, basically, we easily understood that one of these the critical aspects of the parametric performance aspects of floating content is exactly the persistence. Its persistence. The state of the art is mainly focused on the criticality condition, especially the earliest works, basically based on some models and some fluid approximations. They try to derive the function parameter of the service, what is the minimum user density that allows the content to float with very high probability definitely over time. Other important performance parameters of this service are the content availability, the percentage of users that have a content within the anchor zone, the success ratio that can be defined in many ways depending on a specific application which relies on floating content. And one of these ways is as the percentage of users that were given time interval get out of the anchor zone with a copy of the content, which is a measure of the efficiency with which the floating content service makes available the content stored probabilistically to users which traverse the anchor zone. As I was saying, existing results mainly focused on deriving analytical results for critical conditions and for success rate based on a set of mobility models. The problem is that reality hardly matches any of the mobility models which have been taken into consideration. In addition, it emerges from also the studies that floating content performance is highly sensitive to the specifics in mobility models and even to small variations of parameters and characteristics of the service, such as the shape of the anchor zone, the size, and moreover, since floating content service focuses on time scales of the order of hours, in real scenarios, all those parameters of the setting vary significantly typically over time. And this makes it even harder to elaborate models that allow to predict the performance of such a service in realistic scenarios. Hence, it emerges the need to have an experimental approach in order to characterize the performance of such a service in realistic scenarios. So this is what the direction we took. And our first step has been to implement the floating content service on Android applications. What we implemented actually is not an application which the user would interact with, but just the vanilla service, the basic service that just have it presented. Our main aim has been to produce an application which was easily and widely adopted among students in a campus environment. In order to do so, we elaborated it in order to have a very energy efficient operation. So we used Bluetooth for message exchanges and Wi-Fi in order to have a coarse grade but sufficiently good for our purposes localization mechanism. And so this application used visibility of at least one or at least access points in order to understand whether the user is within the anchor zone or out of the anchor zone in our experimental settings. Moreover, in order to have the largest possible amount of points in our experiment, we configured the application in order to have a new content generated every 15 minutes, so a new experiment every 15 minutes. The experiment has lasted a whole week over the computer science building in the University UC3M in campus in Madrid for a total anchor zone area of 7,700 square meters, so a very large one. And during the duration of the experiment, we had a total of almost 1,000 contents which have been replicated, for which basically for the content experiment. What can we see is that this is not a standard floating content anchor zone shape, and moreover, this anchor zone was distributed over 3 floors of this building. So all those aspects which are normally not taken into consideration. Here in this graph, we see over the time of the day, the average over the week of the experiment, the average number of nodes within the anchor zone, that we see is between 9 and 15, as well as with the number of contents, successful contacts, sorry, which take place in 15 minutes interval in function of the time of the day. As we see, these numbers are low. So low that, according to the models, available models, the content should not float, and content should get quickly lost into such an environment, so that floating content would not be feasible in such a context. Indeed, what we observe experimentally is a different reality. So what we see here is per content availability in function of the time from the content generation. And what we can see is that very little number, percentage of the contents being generated during the experiment disappear during the content lifetime, precisely before the end of the day. And moreover, as we can see, the majority of the contents gets replicated to a large enough amount of copies. So we can say that content floats and the availability is not negligible. Is quite enough. So this was one of the interesting data emerging, first interesting data emerging from the experiment. Another observation that we have from this graph is that diffusion proceeds at 2 speed. There's a fast initial diffusion in the first 30 minutes, let's say, or 40 minutes from the content generation, and then another regime of slower growth that continues steadily for a few hours. This suggests that the inhomogeneity user distributions play an important role, at least in this context, for the performance of the content. To further understand the impact of these inhomogeneities and stability patterns, the performance of floating content, we performed the following experiment. We considered the case of contents which were seeded not by a single user, but contents were generated at time t equal to 0 by 2 or 3 different users. And we consider the case in which these 3 seeders at time t equal to 0 are distributed uniformly in space versus the case in which they're all close to each other. So the green and the red curve represent the case in which we have 2 and 3 seeders respectively, uniformly distributed in the anchor zone at time t equal to 0. While the triple curves correspond to the case in which these seeders are close between time t equal to 0. So the difference in performance between these 2 cases, especially the fact that when the seeders are close, the availability over time follows the same behavior as with almost the same behavior when a single seeder, seems to suggest here that the spatial distribution of users is highly clusterized, and there's a very good interaction between users in their clusters. It follows a set of infrequent interactions between clusters happening on time scales of hours, which could be the justification for these 2 different speeds of diffusion. So based on these observations, we tried to elaborate a new analytical model which would be able to predict the performance of floating content in such context, which is based on such features of the mobility pattern. So, and the mobility model we consider is a variation random waypoint in which users have an infinite speed between the two stopping locations. This also because this matches the type of experiment and the technology we use for the exchange of information between users. As the average time taken by content exchanged between 2 peers is experimental 12 seconds. So long enough for having successful on-the-fly exchange of information between, for instance, a user which is still another one which is passive, for instance, in a corridor of the campus. So in our model, we have here an anchored zone, a set of users which are uniformly distributed within the anchored zone, and users jumping into the anchored zone at a rate which matches the mean experimental rate in our experiment. The area here that we consider the anchored zone, we took it to be the same as the total area of the anchored zone in our experimental setting. So when users are in the anchored zone, then with a rate move, they assume to jump into other locations of the anchored zone at random uniformly, chosen uniformly within the anchored zone. Moreover, with probability P, we assume that at each jump, a user might jump out of the anchored zone. And in our model, when it jumps out of the anchored zone, it simply disappears from the scenario. It drops the content, as we saw before, and disappears from the scenario. So, by using this model, we were able to derive a simple formula for success probability. It's a probability of getting out, or a user getting out of the anchored zone with a copy of the content, which we see is parameterized by p-jump, where p-jump is the probability of getting content after a jump. It is a function of the mean density of users with content within the anchored zone and of the transmission radius of the nodes. The three important parameters that we have measured and used in order to parameterize this model have been, as I said before, the rate at which users arrive into the anchored zone, the mean sojourn time within the anchored zone, and the mean time spent by users inside standing still in a given location within the anchored zone. This has been estimated through a heuristic that estimated the clusters from the logs of content exchanges, and from that it estimated the amount of time spent by each user within a cluster. The mean time spent within a cluster is of 58 minutes, and it matches more or less what we could have forecasted by just knowing that it is the average duration of a class in that university. So, by parameterizing this way the model, we derive the values of average availability and average success ratio, or success probability, which are very close to the measured ones. So, this model, despite its simplicity, proved able to predict the performance of floating content in our experimental scenarios, at least for such campus environments. So, in order to conclude, in our work we have characterized empirically some critical aspects of floating content performance, which are relevant for application, which are a first step in order to understand whether it is possible to rely on this floating content service in order to implement application. Also to have an idea what kind of application could be implemented over floating content. In particular, as we saw, clustering, cluster dynamics, such an environment, campus environment, play a major role in the performance of floating content and allow satisfactory performances even at user densities which are normally considered too low for such a service. The future developments, the future directions that we think of considering is considering the performance of floating content from the point of view of one application or a family of applications. Also to focus on performance of a shorter time scales, which is important for at least a class of applications. For instance, hazard, warnings, similar kind of services. Moreover, we will also try to include into our simple model some clustering effects and general effects of correlation between user mobility patterns.
Okay, any question? Okay, thanks for the presentation. This session is end now, and thanks for all of your participation. Okay, thanks.